I'm gonna take you through one of our most important instruments, and which is a basic setup in any drug delivery lab, which is HPLC, standing for High Performance Liquid Chromatography, and which we use for analyzing drug concentrations in our samples. So HPLC is the process of separating components in a liquid mixture. A liquid sample is injected into a stream mobile phase, flowing through a stationary phase, and there are different types of HPLC according to the types of the mobile and the stationary phases. Today I will be talking about the most common one, the reverse phase HPLC, where we use a non-polar stationary phase and a relatively polar mobile phase. Our sample is injected in the mobile phase and then flows over the stationary phase, which separates the sample into its components depending on the affinity and the hydrophobic interactions between each of the sample components and our stationary phase. Here we have the bottles of the mobile phase, which are usually a mixture of aqueous phase with a water-miscible organic solvent. We usually use acetonitrile or methanol as the organic solvent. Here I'm using acetonitrile with 0.1% trifluoroacetic acid solution in water. You can see I'm placing them in two different bottles, and I can control the ratio of both solvents through controlling our pump speed. Here we have our pump compartment. In this machine model we have two pumps, each withdrawing the mobile phase from one bottle, then they are mixed together in the proper ratio. The ratio of the two solvents can be fixed throughout the analysis run, which we call isocratic flow, or can be changed in a gradient run, like starting with high organic to aqueous ratio and increasing the aqueous component over time. This is called a gradient flow. The flow rate of the mobile phase is most commonly set somewhere between 0.5 and 2 milliliter per minute. Since the presence of air bubbles in the mobile phase can extremely harm our analysis, most HPLC systems have a degasser. Sometimes it's integrated in the pump, some other times it's separate, like what we have here, an inline degasser. Here we have two inlets for the degasser from both of the solvent bottles, and then we have two outlets. The mobile phase coming out from the pump goes to the sample injector. Here we have our samples rack, and we place our samples in an HPLC vial like this. We put the rack in its proper place, and here we have the needle which withdraws the sample and injects it into the mobile phase. We have to close the door before starting our sample injection and analysis. This is an auto sampler, so we don't have to inject samples one by one. Instead, we program our software to run a full sequence of samples that can, in this model, be up to 96 samples. The mobile phase carrying our samples then flows over the stationary phase. Our stationary phase is packed in a column, and in reverse phase HPLC it's a C18 column. And the flow direction of the mobile phase here is from down to up. Before passing through the column, it first passes through what we call a guard column, and this is just a filter acting to protect the column from any accidental particles that may be in the mobile phase. This, what we see here, is a column compartment, and it's temperature controlled, so we can adjust the temperature, which of course affects the efficiency of separation. And then of course, before starting our analysis, we have to close the door for temperature control. After separation of the sample components on the column, now it's time for detecting these components and measuring the concentrations. There are a wide range of detectors in HPLC. Here we have a UV detector and a fluorescence detector. We can operate them either together or we can operate only one of them according to our needs. After finishing our run, we get a chromatogram, which is a graph of the peaks we detected in the detector over time. And here in our sample, we have a peak for our drug coming out at time 3.2 minutes, which is called the retention time. We can integrate the peak and determine its peak area. The peak area is correlated to the concentration, and we can use the peak area to estimate the concentration using a calibration curve of standards.